Hi, here is where we stopped in the last video, and in this video I'm going to speak about the fourth section, which is named Atlas, because it speaks in a comprehensive way about Atlas itself, and it magnify the two faces, and it talks about every specific step in each of these two phases. So let's get started without wasting any time. The first thing in this section is called audit log preprocessing, and this is the stage that we build the causal graph in, and we optimize the causal graph. As I've said before, optimization is something essential because once you have recorded your audit logs, eventually you will find that the causal graph contains millions of logs, millions of nodes, entities, actions, events. So you have to optimize this causal graph so eventually your algorithms work in a proper manner and do not take that much time. So how the complexity is reduced actually, it's written here that we built optimized causal graph to reduce the log's complexity, which means reducing the number of nodes and edges. So this is how it is reduced. And there are three techniques for graph optimization. The first technique is to eliminate the nodes and edges which are not reachable by the attack nodes. Let's assume that we have an attack node and there are millions of other nodes, but this attack node do not have a path to the other nodes. So we don't have to give much care about the other attack nodes. If they are not reachable, so I'm going to discard them from my model. And the second option we have is that Atlas constructs the causal graph from audit logs with non-repeating edges. As you can see in this image, this is a repeated edge. So I can discard the three edges into one edge. Also, I can discard these three edges into one edge. Finally, I can discard these two edges into one edge. So what is the difference between here and there? So here I have same source, same destination, and same action, but the difference comes in the time. So I will discard the late event, and I'm going to take into consideration the first early event, which is T2, not T9. And here I will discard the three edges and I will minimize them to one edge, but I have conditions. The three edges must contain the same action, the same event, which is bend, and all the nodes that are shared between the destination and source have to be the same, so that I will conclude them in one node. And by applying these methods, eventually I will have the ability to reduce the number of nodes and edges by 80%. So if I have 800 nodes, I'm going to make them 20 nodes only. As you can tell, if I have 1 million, they are going to be 200k, etc. So this is brilliant actually. And the second thing we have in the large phases is the sequence construction. Actually, how are the sequences built? And this is a little bit complicated because it has two ways, the attack sequences and the non-attack sequences. And for attack sequences, we have to take into consideration that the attack entities are the ground truths. So other than the attack entities, I consider them non-attack entities. And another note to take into consideration is that the attack entities here are the ones that can only be associated with attack events. We are going to elaborate this in a proper manner, but I have to tell you what is an attack sequence. What does it mean? Attack sequence. The attack sequence include temporally ordered events. So they are events, but we order them by the time of occurrences of these events. And Atlas first obtains the set of all attack entities from the causal graph and construct their entity subsets. So we have a lot of attack entities, so we create subsets of these attack entities that include two or more entities. To elaborate this more, we are going to be focusing on this graph. Let's say that this is the causal graph. This is the whole causal graph. And I'm focusing on from A to C. So I will extract this attack subset from A to C and their neighborhood. So I'm not going to take into consideration E because it's not a neighborhood. It's not attached to C directly, and it's not attached to A directly. And from this neighborhood graph, I'm going to create the sequence of events by temporal order: T2, then T3, then T4, then T5, and finally T6. Because this is the time of occurrences. So this is defined and labeled as an attack event, an attack sequence. But by extracting the other sequence, which is from A to B and their neighbors, which is C only. So we have this. We discarded these because they are not attached directly to A and B, and we want to measure this to the ground truth. The ground truth, as we said, is this sequence. So anything like this sequence is going to be detected as an attack. But this sequence differs from this sequence. It's not completed. So now we have a non-attack event, a non-attack sequence. So the neighbor, eventually, we have causal graph, we have neighborhood graph, and from the neighborhood graph we create sequences, and finally we compare these sequences with each other, and we determine whether they are attack or non-attack. How can we determine that this is attack when the whole sequence contains the entities that are considered attack? So this sequence contains really A, C, F. So now I can make sure that they are considered an attack. So this is how we determine that this is an attack. Talking about the lemmatization, which is all of these. Like, let's recap. Here we can't apply the same methodology in non-attack sequences, because why we can't apply the same methodology of non-attack sequences with attack sequences? Actually, because I have so many non-attack sequences, so I can't follow this methodology. I can't just compare the new non-attack with the attack. So this is how we do. And here, yeah, simply it is variable and depends on the causal graph. Yeah, so here where some information about the sequence length and the number of sequences. Actually, they are not independent. It depends on the causal graph. If the causal graph is huge, so this sequence is going to be larger than 6 sequences or 6 events. Here are 5 events. But if it is small, this is going to be smaller in length. Moving to the lemmatization. Actually, what is the meaning of lemmatization? It means in general in NLP, lemmatization means to reduce the number of vocabulary in the dictionary, which means that the word run, for example, the past symbol of run is rain, but they have the same meaning. So lemmatizing the word rain is going to be converted to run. So now, if I had the word run, it's not going to be lemmatized, but the word rain is going to be lemmatized to run, etc. This is in general, but in this application, the lemmatization happens. I believe that you are going to understand exactly how the lemmatization happens with this example. For this example, I have an event, I have a source, and I have a destination. So the source is this directory to this file, and the event or the action is reading. And reading what? Reading this directory to this PDF. So what I'm going to do is transforming this to this simple sentence that contains a semantic meaning. System process reads user file. It has a semantic meaning that you can understand yourself with your human brain, and also the model understand the semantic meaning while computing their embedding relative. So eventually we are going to convert all the sequences into sentences that contains semantic meaning. And here is the vocabulary. As you can know, English has tons of words, and let's assume that Atlas has 30 words. It is mentioned here that it only contains these 30 words, but actually I counted them by myself and they are 28 to 29 words only. I don't know what is the word that is missing. Maybe the other could tell, but this is the vocabulary. Maybe there are 4 categories. You can consider them like in English. This is the category of vegetables. It contains the word apple, the word orange, etc. And here is the category of actions. They contain read, delete, write, execute, etc. And so on for other words. So moving from lemmatization to selective sequence sampling. Actually, in this process, this is very innovative because in selective sequence sampling, you are required to increase the number of attack sequences and decrease the number of non-attack sequences without harming the dataset. We have to get rid of the unbalanced dataset. How? By oversampling. How does oversampling happens? This is done by mutating the attack sequences. Let's assume that this is an attack sequence. System process, read, user file. What would happen if instead of using system process, we are going to use this vocabulary? Lib process, which comes from library process, for instance. So lib process read user file. So this is could be considered an attack event, an attack sequence I could add to my database so that I can increase the number of attack sequences. And for undersampling, how could we reduce the number of attack sequences, non-attack sequences, because they are very huge. Actually, this is done not by this is done by an algorithm that is called Levenshtein distance. Levenshtein distances, it measures the similarity between the sequences, and for the very identical sequences, we discard some of them. Let's say that I have three sequences that are 80% identical. So I can discard the other two and I can keep only one sequence to train my model on. And how it works, actually I searched on how it works and I found out that if I have the word kitten, which is written in this way, kitten, and I have the word setting, how can I measure how much they are similar to each other? I'm going to iterate on the word kitten and character by character, and I will compare. So the word kitten, for the K and S, do I need to make any substitution? The answer is yes. So the cost is 1. I have to substitute K with S. So the cost is 1. And for I don't have to change anything. For the double T, I don't have to change anything. But for the E, I have to change it. So the cost is 2. And for the G, N, I don't have to change anything. For the word, for the character G, I have to add G here. So that eventually I have a cost of 3. So this is how I train. This is how I know the similarity, and using this algorithm, I can know how much the sentences, the sequences are the same. So I can determine whether I can discard or not. Based on what? Based on certain threshold, which is 80% similarity. If the two sequences are 80% similarity or similar or more, I can discard them. So this is how I calculate I determine the oversampling and undersampling. And finally, the sequence embedding. There are several algorithms of embedding, of word embedding and sentence embedding, such as GloVe, Word2Vec for word embeddings, Sent2Vec, Doc2Vec for sentence embedding, and even transformers are used in this manner. But what the author used here is Word2Vec algorithm, and this is done by giving the model the words, and it generates its embeddings based on the training sample. I'm not going to dig into details about the embeddings. If you can ask me to do some videos about Word2Vec embeddings, if you are interested, and how the model is trained on generating the numbers that represent the words. But the question is, why to do embeddings? Embeddings means to make a representational numbers for each word in the vocabulary of the dictionary. Why? Because NLP models deal with numbers, not with text. So this is why we are doing the embeddings. And this is what are the embeddings. Let's assume that they are just features. Numbers correspond to features that represent the word. And each word has corresponding 128 word to describe this word. So this is how, this is what are embeddings and how we acquire them using Word2Vec algorithm. After acquiring the embeddings, we feed them to the model to train the model on the sequences with their labels. So I have the sequence, which are represented in embedding, its corresponding embedding. So I feed the LSTM. Why LSTM? Actually, we're going to talk about why LSTM, but for now, it is because it takes into consideration the sequence's positions, and position here means when it happened. It happened, which one came first. etc. So this is how it is. And finally, for this section, which is named Atlas, how is attack investigation happened, which is the second component in the overview. Attack investigation happened when attack symptom entity occurs. So it starts after an attack entity symptom occurs. I have to study the unknown entities around them, and I have to determine which unknown entity that is attack and which is non-attack. How? By adding to the attack symptom the surrounding entities, and build the sequences and feed these sequences to the model, so that the model can predict whether it is an attack or non-attack based on the memory that it has, because the model is trained on the attack sequences, so it knows whether sequences are attack, and it's trained on the non-attack sequences, so it knows whether which sequences that are non-attack. So this is in a simple way. What is the goal? The goal from Atlas investigation phase is to recover all the attack entities related to the given attack symptom. And I've just told you how this happens by feeding the sequences, building the sequences, feeding the sequences to the model. But how can we build the sequences? This is done by traversing, and traversing is of complexity O of n. And while traversing, let's study this. Let's assume I have these attack alerts. So I'm going to build the neighborhood graph, which is optimized. So I will take into consideration these entities only. And I have two main if conditions. The first, if non-attack entity reads from an attack entity, so it's going to be considered an attack entity. So for example, this entity reads from this entity, so I'm going to consider this an attack entity. And the second if condition, if non-attack entity, like indexer for example, fork from non-attack entity, so it's fine. Non-attack from non-attack is going to be considered non-attack entity. And this is how we determine whether if this attack or non-attack. And finally, to make it easier for the cyber analysts, we build the story of the attack sequence. So we can, by traversing, I can know where did this come from, and where did this come from. So I can build this sequence so that the cyber analyst determine whether it from which direction it comes from, and it can analyze the cyber attack. So this is all for today's video. We covered the section number 4, and in next video I'm going to cover the implementation, which doesn't contain that much important information. It just talk about, we used Python 3.7, we wrote about 3,000 line of code, etc. They are not that important, but most importantly, we have to know how did the author evaluated his method, because this is a very important part, but we are going to, for the sake of ease, talk about this next time. So thank you so much, and if you have any question, just drop a comment, and thank you. Goodbye.